Dear student, we are going to perform the analysis of the step bar in ANSYS APDL. So the problem statement says that we have a step bar in which we have two cross sections. So section 1 contains an element having a diameter of 15 millimeter and element 2 has a diameter of 10 millimeter. So we are going to define the nodes based on the distance. So node 1 is at distance of 0 0 in for the Cartesian coordinate system, and node 2 is present at distance of 180 millimeter, and node 3 is present at distance of 380 millimeter, so 200 plus 180. And then we have element that is in between. Element 1 is in between node 1 and node 2, and the element 2 is in between node 2 and 3. So first we are going to calculate the area. So for the area for element 1 is 5 by 4 d square, that is 15 square, that is 176.714, and element 2 contains the area of 78.54. Then we have displacement. So node 1 is at 0, node 2 is at 180, and node 3 is at 380 millimeter. So starting with uh, this change the job name, that is a step bar. So type of the analysis we are performing is the structure analysis, and define the element type, that is at we are going to define the length 3D finite 180. So after defining the element, define the material properties. In material properties, material model, structural, linear, elastic, and isotropic. So that is 2 e power 5, and Poisson ratio is 0.3. So that is given within the problem statements that the Young modulus is 2 e power 5 for both the element 1 and element 2. So next step is we are going to define the sections. So we have to define the area for both the elements. So at element 1, okay, and for the element 1 we have a link area of 176.714, and similarly we are going to define the second cross sectional area type 2, and that is 78.54. So 78.54. So next task is to define the nodes. So we are going to define the modeling, create nodes, and an active coordinate system. First we are going to define the node 1, that is at 0 0 coordinates. Then we are going to define the node 2, that is at 180 millimeter, and then we are going to define the node 3, that is 380 millimeter. So you can confirm this in the problem statement that node 1 is at 0, and node 2 is at 180, and node 3 is at 200 plus 180, that is 380 in x direction. So after that we are going to define the elements. So first we check the selected element attribute is material 1, and we have section 1 defined. Okay, click on auto number through nodes, select node 1 and node 2, then first element is created. For the second element that has different cross sectional area, so we have to define the element attributes first. So select the section number 2 for the element 2, and then click on 2 nodes, check 2 and 3, and 2 elements are created. You can counter check these properties in list, element, and nodes and attribute. So we have 2 elements, we have one material assigned to both the elements, and we have section 1 is assigned to section element 1 and section 2 is assigned to element 2. So element 1 is in between node 1 and 2, and the element 2 is in between node 2 and 3. So next step is to define the loading. In the loads menu, click define loads, apply. So first we have to define the displacement on nodes 1, that is fixed node. We are going to define the RDUF and put the value to 0. So node 1 will be fixed. Next step is to define the forces. So at node 2 we have 5000 kilonewton in compressive force, and on node 3 we have 2000 newton in compressive direction. So this is the load table, that the node 2 contains the minus 5000 newton force and node 3 contains the 2000 newton force. So to apply the this force, go into structural, then force menu. On nodes, select node 2 as it contains 5000 force in negative direction. In x direction, click OK. Then 5000 force will be applied in negative direction. So then click on node 3 and apply the 2000 Newton force. Click OK. So you can counter check these loads on list nodes and forces on all nodes. So node 2 contains minus 5000 Newton force and node 3 contains minus 2000 Newton force. So now close the preprocessor and go into the solution, solve and current ls. OK, and the solution is done. So next step is to extract the result in general post processor of the APDL. So first click on the plot result, then click on the contour plot and nodal solution. Then click on GOF solution and X component, OK, and you will be getting a maximum nodal displacement. So to find the all the nodal solution, you are going to click list result, nodal solution, then again X component of the displacement, and you will be getting a nodal solution on node 1 that is fixed. That is why it is 0. Node 2 contains the minus 0.35 because it is minus 10 to power 1. So minus 0.0611. So we are going to compare it with our analytical solution, that is U2 is minus 0.356 and U3 is minus 0.611. So it is pretty same. That is the analytical solution, and that is the FEM solution, approximate solution that we are getting from the ANSYS. So next step is to calculate the stresses, that we are going to define the element table. Click on define table and click add. Now we are going to by sequence number select ls, 1, click OK, and to check the stresses we are going to go into list result and click on element table. So you are going to find ls1 that we have already defined, and you are going to get the value of sigma 1, that is 39.6, and sigma 2, that is 25.465, nearly equal to 25.5. So we are going to check with analytical solution. So the analytical solution for sigma 1 is 39.5. So we are also getting a 39.6 here. And for the sigma 2 we are getting 25.5 negative by mean of the analytical solution, and through ANSYS we are getting minus 25.465. that is pretty close. So if you are going to, so we are going into plot control, style, size and shape, and check this menu on, and you will be getting a 3D view of a object that is in the compressive load. Thank you guys.